My name's Cameron. I'm just going to talk to you about the PhD project that I'm getting to the end of now with the NextCom program grant, where I'm looking at single fiber micromechanical analysis and compression using a spectroscopic technique, in this case, Raman. So a very quick introduction to composites in compression. The compressive strength of composites is often 60% or less than the corresponding material's tensile strengths, and obviously this is quite a big disparity in the strength. So when we're designing parts for compressive applications, obviously it's a critical design consideration that you need to take into account. So NextComp is looking to improve this, trying to double the compressive strength of fiber reinforced polymer composites. And my particular area is looking at compression of single fibers and the fundamentals of how the interface is behaving, how they're failing, and how we can improve our understanding of these processes to hopefully improve the compressive performance of the composites on a fiber level. So from work in NextComp, we know that the interfacial shear response of our fibers is critical, which is somewhat of an issue for compression because there's not very many ways to investigate the interface in compressive loading. So this is something we want to do. Single fiber testing, if anyone's done it, you probably know it's quite experimentally challenging. And we also want to look at how our single fibers are failing in compression. So we're using Raman spectroscopy, which very quickly is a spectroscopic technique where we're looking at vibrational information in the atomic structure of our carbon fibers, in this case, in the graphitic structures, where we shine a laser on it and we collect the scattered light, and we can tell atomic structure information from the scattered light, which is the difference in the frequency of the incident versus the scattered light. And we're mainly interested in what we call the G band, which is the band due to the graphitic structure of the carbon. And we know that this will shift to higher Raman wave numbers when we compress the bonds in the graphite, and we can track this shift in the G band and relate that to strain, and then we can use that shift to calculate stress in our fibers. So Raman spectroscopy is a very effective stress sensing technique for graphitic materials in particular. So now that we have our G band calibration, so we know our stress from a shift in the G band, we can do some spatially resolved stress mapping by collecting spectra along a length of short fiber with the ends in the epoxy, using this setup here where we have a Debye stage in our Raman spectrometer, and then we will scan along it, collect the stress at certain points, and we will map that, producing a map such as this seen on the left, this is for a length of M46J high modulus fiber. And we can see when we increase our loading and the resulting strains, we get an increase in the stress along the fibers with a nice Cox type shape, where it increases from a minimum at the ends up to a maximum in the center. And if we fit our micromechanical model to this and then use a balance of forces approach, we can derive our interfacial shear stress characteristics. So we can see from this we get our maximum interfacial shear stress of around 23 megapascals and a transfer length of around 400 microns. Another very interesting thing we can do with this is we can look at how fragmentation occurs in high modulus fibers in compressive failure, and we can track how the fragmentation propagates from initiation to eventual compressive failure. So future work, we're going to be changing our interface of our fibers and seeing how that's behaving in compressive loading, and we also want to do some bit more micromechanics to see what's actually going on during the compressive failure of high modulus carbon fibers. So if you have any questions or further questions or want to know more, please come find me at my poster, but otherwise, thank you.